Okay. Assalamualaikum warahmatullahi wabarakatuh. Very good evening. Can you all hear me?
Yes, doctor.
Yes, doctor.
All right. Okay. Thank you very much for joining. Again, I think we are continuing to chapter 4 today. Uh, Also, I've already closed down your assignment punya drive. So at the moment, I only have 27. So there's 4 of you who didn't submit your assignment 1. So those who didn't submit, please do submit by tonight, before 12 o'clock. So anything after 12 tonight, I will not accept. Okay. So for those who already submitted your assignment 1, thank you very much for submitting on time. I really appreciate that. So let's move on to chapter 4 today. Okay. Actually, I really wanted to finish chapter 4 by tonight, but because it's the first night of Ramadan, so probably I'll finish off by 9 o'clock. So I think most of us will be. And it's yeah, so most of us can actually do Tarawih up to 9. So I'll be finishing by 9 o'clock, but we'll continue back next week. Okay. So so let's move.
Doctor. Doctor mute.
Sorry, how long was I mute?
I think 5 seconds. Yeah.
Oh, okay, all right, okay. Okay, so moving on to chapter 4. But I already told you that we're finishing off at 9 o'clock, right?
Yes, yeah.
Yeah, okay, right, great. So do remind me if it's 9 o'clock, just in case I got carried away. Okay. Tonight is chapter 4. It's about engine cycles. So under engine cycles, it will split into 3 chapters, which is the air standard cycle, Otto cycle, and also diesel cycle. So definitely, Otto cycle or diesel cycle, okay, Otto or diesel cycle will come out in your test. Okay, will definitely come out in your test, and probably will be coming out in your exam as well. So you really need to understand this. You really need to know how to solve questions under engine cycles. Okay, but it's pretty much straightforward. It is, I would say, an extension of the thermodynamics cycle, like Carnot. It's nothing new. It's just extension of whatever you have learned in thermodynamics. So we'll start off with air standard cycle first. Okay. So this is a quite popular picture. I think most of you have already seen this. What as a mechanical engineer, what my friends think I do, what my mom thinks I do, what society thinks I do, what the government thinks I do, and what I think I do. So those are all assumptions, okay, from different perspectives, from your friends, from your mother, from the society, from the government, and also an assumption of how you assume yourself. But in reality, it's pretty much different. So the point of the story is basically, in order for you to learn the actual cycle of internal combustion engine, you will definitely need to do some assumptions. Okay, you really need to do some assumptions. Because the actual cycle on internal combustion engine is very complex. Okay, So, let's just go through very quickly. What's the difference between the actual cycle and what's the difference between the air standard cycle? So, actual cycle, in other words, is the actual engine combustion cycle that happens in the actual engine. It's a variable complex composition of combustion with of course, with mixtures, CO2, H2O, N2, and so forth. Okay, and the actual cycle is an open cycle. Okay, what it meant by open cycle is basically you rely on there's a fresh air intake that goes into the cycle, combust, and then it is expelled as exhaust gas. So it's an open cycle. It is not being recycled. Okay, it's an open. So fresh air will always comes into the combustion. Okay, and whatever burn gases will be expelled out, and it won't be returned back into the. So it's a open circle, open cycle, which is very complex, very complex. Which is why they have created this air standard cycle for many purposes. Among the main purposes is for education, for you all to learn, and for analysis purposes. Okay, so air standard cycle is basically a simplified version of the cycle. Okay, it is manageable and it helps to determine important design parameters. So in other words, it is more likely to be solved or to be understood, okay, rather than an actual cycle. Because in actual cycle, very complex, okay, which is why we need to learn and really understand about air standard cycle. Okay. So since we know as air standard cycle is not real, but it is an ideal case. It is in a perfect condition. So therefore, to work on the air standard cycle, you must first understand the assumptions that needs to be applied. These assumptions needs to be understood and really, in order for you to really understand about air standard cycle. Okay, these assumptions are the law and also the principles of air standard cycle. Okay, because otherwise, if you don't understand the assumptions, then you will definitely never, you will, it will very difficult for you to understand the air standard cycle. So certain assumptions need to be made in order for you to solve the air standard cycle. So what are the assumptions? Okay. Okay. These are we're gonna go through some assumptions. Okay. You really need to understand this because otherwise it will be very difficult. Okay. What are the assumptions? Okay. Assumptions in a perfect world, in a perfect cycle. So working fluid is purely entirely air, which is not true in actual engine because you have a mixture between a small mixture of water and also an equivalent mixture of fuel, right? So, but in air standard cycle, you need to assume that the working fluid is entirely air. Okay, it is a closed cycle. Okay, it is a closed cycle. It is a closed cycle whereby the gases being exhausted are feed back into the intake system. In reality, it doesn't happen like that. Whatever that is being expelled as exhaust gas, it will never return lah. And fresh air is always coming through into the combustion chamber. So it's a in the actual cycle, it's an open cycle, but on the air standard cycle, we assume it is a closed cycle. It's always closed. Okay, so whatever is being expelled, it will go back into the air intake. Okay, apa yang dia berak, yang itu dia makan. Okay. No combustion for this air standard cycle. Okay, for air standard cycle, we assume there will be no combustion. Okay, there will be no combustion, but the compression and the expansion still happen. Okay, okay, and then the combustion process is replaced. Okay, the combustion process is replaced with a heat addition terms as Q in, energy in, heat energy in. Okay, I'm sure that you all already familiar with Q in thermodynamics is the heat energy in of equal energy value. And so the open exhaust process is replaced with a closed system heat rejection or energy out. Okay, Q out. Okay, so there's energy in, which is Q in, and also energy out, which is Q out. Okay, and it consists of many ideal processes. Okay, and among the processes, constant pressure exhaust at 1 atmospheric. Okay, 1 atmospheric is equivalent to 1 bar. Yeah. Natural aspirated cycles have constant pressure intake at 1 atmospheric. Okay, whereas for forced induction, turbocharged and also supercharged, have a constant pressure above 1 atmospheric. But in the case for us to learn, we will mostly use an A cycle. Okay, for if it's a natural aspirated engine, exhaust and intake will always be at 1 atmospheric. So in other words, this value is 1 atmospheric. Compression and expansion process are isentropic. Okay, I don't want to teach you about isentropic. By now, I think you should be able to understand what is isentropic. But just in case you forget, you can always refer back to your notes on thermodynamics. Okay, with use constant specific heats. Okay, specific heats will be using constant. Okay, a figure, a constant figure. Heating is at constant volume for spark ignition cycle. Okay, for heating for is at constant volume. Okay, but on compression ignition cycle, heating is at constant pressure. Okay, so those are the important things, because later when we go into auto and also the diesel cycle, then these two uh, terms or phrases will be relevant for you to you can actually witness what is it meant by constant volume and what is it meant by constant pressure. Cooling heat rejection is at constant volume. All processes are reversible. Okay. Also, you also need to understand what is adiabatic processes, isotropic processes, and so forth. So these are some of the common terms you already supposed to be familiar in thermodynamics. So if you look at the atypical air standard cycle, you have all the four strokes. You start with the intake stroke, whereby the pistons moves from TDC to BDC. So you have the intake stroke, and then after intake is the compression stroke. Okay, and then once the compression stroke starts to compression stroke is from point 1 to point 2, and in this case, remember that there's no combustion, and because and this is where the Q in energy goes in. This is actually happens at a constant volume. Okay, the pressure increases, but the volume doesn't increase. And then it follows by the expansion process from point 3 to point 4, and as it reaches point 4, energy goes out, which is Q out. Okay, Q out, and in this process pressure drops, but okay, there's no increase of there's no change in uh, volume. But for the exhaust stroke, yes, the volume changes, but there's no changes in terms of the pressure. So these are some of the rule of thumb in air standard cycle, which you some of the basic principles that you need to understand first, okay, in order for you to solve problems later or questions. Okay. So in air standard cycle, because the fact that is an ideal cycle, we treat the gas as an ideal case, which is being governed by the ideal gas law, which is PVMRT. Everyone knows that, and of course, there are certain terms that you will be used under the ideal gas conditions. Okay. All of these formulas, okay, some will be given in your exam, some won't. Of course, you need to familiar lah. Okay, once you start to do your exercises, okay, then you start to familiar with all these terms. These are some of the meaning abbreviations of the symbol which will be used, like speed of sound. What is the symbol speed of sound? What is CP? What is CV? Specific entropy, M, T, R, V, small v, big V, capital V, and capital P, and so forth. So these are some of the guidance lah. So using the constants below, okay, air standard cycles also requires for you to use constants, which is sometimes available, provided. Most of the time it will be provided, such as the specific heat, specific volume, okay. These sometimes, some of the questions will be given, some are not, okay, some are not, okay. So of course, especially K, this one definitely I know will not be given. So if the formula requires you to use K, then you definitely you need know lah, it's 1.35. Okay, and of course R, everyone knows R is 0.87 kilojoules per kilograms Kelvin, and of course CP and CV most of the time will be given. But yes, what you should do, okay, before our in later I will provide you the list of formulas that will be provided in your test and exam, so that you know what will be given and what will not. Okay, later I'll pass you the list of formulas. So that is pretty much on air standard cycle. Okay, air standard cycle is just an understanding for you to move on. It's a prerequisite for you to move on into auto cycle and also diesel cycle. Okay. Again, like I mentioned you earlier today, auto cycle question and also diesel cycle question is among the popular questions included in your test and also exam. Yeah, whereas air standard cycle is just a basic understanding for you to move on into auto and also diesel. So far, any questions before I move on into auto cycle? Okay, kalau tak ada, let's move on. Can I move on to auto cycle?
Kan, Doktor?
Okay, thank you. So, this is the chap lah, Nicholas August Otto. Okay, born in 1832, meninggal in 1891. So Otto built his first gasoline power engine in 1861, but developed an improved version and won the gold medal in Paris Exposition in 1867. And in 1876, roughly about 9 years later, Otto built the ICE utilizing the four-stroke cycle, but was patented in 1862 by the French engineer Alfonso Bois de Rochas. Okay. So since Mr. Otto was the first to build an engine based upon his principle, it is commonly known as the Otto cycle. But unfortunately, it was patented by other person. Sad story, but so that is pretty much about Nicholas August Otto. So let's talk about Mr. Nicholas August Otto's cycle, okay, which is commonly known as the Otto cycle. So again, we would like to simplify the actual cycle. If you look at the real actual cycle, okay, it's pretty much quite complicated, okay, because there's so many complex composition and characteristics of combustion and so forth. So therefore, we need to make it simplified and based on this auto cycle. Okay, definitely when you measure this is basically the PV diagram. I'm sure you're already familiar with the PV diagram in thermodynamics. So if in the case of where you stuck one pressure transducer in your combustion chamber and measure the pressure against the volume of the piston, okay, in actual engine, then the cycle would look like this. Okay, this the characteristics of the pressure against volume will look like this. Okay, which represents the four-stroke cycle. But in the case to simplify the cycle to make it more understandable and also manageable, then comes this auto cycle. Okay, if you look through, it all started with, okay, whereby piston with intake stroke. So piston starts with piston position starts at TDC, moves to BDC in intake stroke. Okay, bear in mind that we assume in air standard cycle that it is always at 1 atmospheric. Okay, here 1 atmospheric, and after the intake stroke is the compression stroke. Okay, so compression stroke starts from over here to point number one to point number two, and point number two to number three is where the energy goes in. Okay, Q in. Okay, and then bear in mind, looking at this graph, you could see that the pressure significantly instantaneously increases at a constant volume between point 2 to point 3. And then after point 3, as the compression stroke finishes, it follows by the expansion stroke. So point 3 to point 4, this is, and from point 4 to point 5, this is where the energy that goes out, Q out. Okay. Again, during this, there's a quick release of pressure at a constant volume, and then point number 5 to 6 is whereby again during the exhaust stroke, we assume that the pressure is always at 1 atmospheric. Okay, so that is pretty much the four-stroke cycle explained in terms of auto. Okay, a simplified version, of course. But if you measure your pressure in an actual engine, you will never get this. Okay, if you measure your engine, you will always get this. But for learning purposes, we're gonna use auto. So let's go through. You really need to understand these processes because this is a common thermodynamic question. Okay, a common question will ask you to solve this problem. Okay, so in order for you to solve this problem, we need to know each of the process. Okay, overall, even though there's four strokes, but there's six processes that is happening under the auto cycle because if you look at from point 1 to point 2 to point 3 in actual life, this is actually from point 1 to point 2 to point 3 is the compression stroke. Okay, and the expansion stroke or the power stroke should be between point 3 to point 4 to point 1. Okay, 3, 4, 1. But in this case, auto, it breaks up. Okay, the constant volume heat addition separately from the compression stroke, and it separates the constant volume heat rejection, okay, from the expansion stroke, which is why you have six processes. It is still four cycle, but in this case, we are treating it is no longer we treat that as a cycle, but we treat that into processes. Okay, and processes which involves there's 6 points. Okay, so isentropic compression. We always start with isentropic compression, whereby point 1 to point 2, and then you have the next process is point 2 to point 3. This is the constant volume heat addition. This is Q in, and then you have the 3 to 4, which is isentropic expansion, and then 4 to 5 is the constant volume heat rejection or Q out, and then you have 5 to 6, which is the exhaust at ambient pressure. and then you have the intake at 1 from 6 to 1. But it doesn't really matter whether you want to have those labels in a different order. You can start at 6 to 1, or you can start at intake at the above. Doesn't really matter. Okay, but it has to follow accordingly. Yeah. So the fact that most of the questions we assume it's a natural aspirated engine, so don't worry. The intake and also exhaust will always be at ambient pressure or 1 atmospheric. Okay, forget about force induction. Okay, so those are the 6 processes. Okay, in order for you to solve this thermodynamic process, you need to understand what are the formulas for each of the process. Which formula you want to use for each of the processes. For example, what is the formula you need to use in isotropic compression? What are the formula you need to use in constant volume in addition? And so forth, so forth, so forth. Okay. So, in the case of whereby a question will ask you to solve a thermodynamic analysis based on Otto cycle, the first thing you all should do is plot this graph exactly like this. Label all the graph 2 to 3, 3 to 4, or 4, 5, 1. If you are able to plot this graph, okay, then you should be able to know what are the process involved. Okay, that's my first tip. Now, again, if there's a question asking you to do thermodynamic analysis, the first thing you should do is plot this graph. This graph should be able to guide you. Okay. Okay. So let's go through. So let's go through the PV diagram. Okay. So of course, we are concerned on the PV diagram. So most of the thermodynamic analysis will be based on the PV diagram. It's well, we hardly touch on anything on the entropy diagram, TS diagram. Okay, so it's more towards this just to show us, just to recap lah. I think most of you already know what's the difference between PV and also TS diagram. But in this case, we're going to use PV diagram lah. So let us apply the applicable thermodynamic equations just now at load conditions, a thermodynamic analysis, and on air standard Otto cycle. So in other words, first things first, you need to again, it is split. This is what basically I explained to you. Originally, there's 4-stroke cycle, but the fact that we are analyzing the thermodynamics based on air standard Otto cycle, it is break to processes, 6 processes. Again, what you should do first things first is plot this graph. Okay, do practice how to plot this graph. Okay, it's very pretty much quite straightforward. If you're able to plot this graph, then this graph should be able to guide you on solving the question. Okay, so let's go through first. One is basically, okay, number one, it is, let's go through each of the process. Okay, so the first process is intake, 6 to 1. Okay, so the piston moves from point 6 to point 1, and piston moves from TDC to BDC. Okay, so during this process of intake process, both the intake valves are open. Okay, so you need to understand that T1, pressure 1, pressure at the position 1 is equivalent to pressure at point 6, which is equivalent to 1 atmospheric. So you know, actually, because even though the piston moves from TDC to BDC, pressure actually is constant. Okay, so you can say that the pressure at 0.1 and 0.6 is equivalent to 1 atmospheric. Okay, because we assume it's a natural aspirator lah. Don't worry, just assume it's natural aspirator unless otherwise. Well, with force induction will definitely not be included because it's it's too complicated. And then, so therefore, in order for you to calculate the work for the piston to move from position 0.6 to 0.1, pressure 1 atmospheric times the specific volume of V1 and V6. Okay, that's pretty much quite straightforward. So in process 1, which is 6:1 intake, what you need to ask yourself, what is the pressure? What is the how much work it can be is being produced during this process. Next process is the compression stroke. Now it is slightly after the intake process, then it is the compression process where the point moves from point 1 to point 2. This is how you calculate. So it involves it requires you to measure what is the temperature at point 2 and what is the pressure at point 2. Okay, so you can actually use these formulas over there. Of course, you know that K is 1.35. So hence, you need to always remember what is K. Sometimes it's not provided lah. But because T1 T1 most of the time it will be provided in the question. You already know V1 and V2, which is probably provided by the size of the engine and so forth. That should be able for you to calculate T2. And of course, you need to measure. You also need to calculate the P2. So, and of course, you assume that there's no heat being in or out. There's no heat involvement in this case. And to calculate work, you can either use based on the ideal gas law, or also you can use based on the constant using constants and also using specific heat and so forth. Depends on which parameters that is provided, then you should be able to decide which formulas you should use. Okay. Then comes the it is during so-called the combustion process, but in this case we assume that there's no combustion. All that happens is there's energy that is provided, okay, at a constant volume. So the process starts from point 2 to point 3. You can see that during this process, the volume is constant, okay. And during this process, energy is being provided, heat energy is provided, and you can actually calculate based on these equations. Okay, so that's pretty much, I think most of you already familiar, have seen this in thermodynamics. Okay, QHV is the heating value. Okay, mass flow and so forth. MA is mass of air, and MF is the mass of fuel. So, okay. So in this case, I'll try to make it very straightforward for you to practice this. Okay. So that is pretty much on combustion 2 and 3. These are the formulas that is relevant under this process. Okay, I won't take your time to elaborate each of the formulas, but those are the formulas that will be related later when you do the exercises, which I will give you towards the end of this class by 9 o'clock, so that you can actually have a go and try and see whether you can solve the equation, the problem or not. Okay. Next is the power expansion stroke, where the piston moves from TDC to BDC from point 3 to point 4. So those are the formulas that is relevant and may be required for you to calculate T4, P4, work from 3 to 4 and so forth. Okay. And then this is where the energy that goes out, or in other words, it is called as exhaust blow down process. So it moves from point 4 to point 1, point 5 at a constant volume. Okay, so those are the formulas that is related under this process. Again, you can because the fact that volume is constant, so V4 and also V5 is always the same because it's and also V1 of course. This is actually the volume of where the piston is at BDC. And of course, there's no work because why there's no work? Because there's no movement, okay, of piston under the process of four to one, okay. Of course, there's heat energy that goes out, which can be calculated this using the temperature of mixture and also specific heat. So those are the formula related under this process. Next is the last process, which is the exhaust process. Okay, is it the last process? Yeah, yeah, it's the last process. So piston moves from point 5 to point 6. So whenever there's movement, there's always work involved, and you can calculate the work based on the pressure and the difference of volume, and of course P5, P6, and also P5 and also P6 is always at atmospheric, because remember, exhaust and intake will always be at the 1 bar or 1 atmospheric pressure, or in this case it's natural aspirated. So that is pretty much the 6 processes. Each of the process in this slide, the related formulas is already given to you. Okay, so this is what we call as we have just gone through the 6 processes, and once you have calculated everything, then you've already completed the thermodynamic analysis. Again, ask yourself here, okay, are you be able to draw this figure or not? Because this is the first step you should do before you start to solve each of the processes. Okay. So basically you have done the thermodynamic analysis. What's next? So after you have solved this problem, then comes the question, can you calculate the thermal efficiency? Yes, because most of the parameters for you to calculate your thermal efficiency, okay, most of the parameters over here, you've already calculate in your thermodynamic analysis. So by applying these formulas, you can actually calculate your thermal efficiency. So only cycle temperatures need to be known. The equation can be simplified further by applying ideal gas relationship. Okay, so if you could see that the some of the equations he uses over here, well, it's pretty much the same. Okay, depending on what is actually given to you and what is available for you to calculate your thermal efficiency. So this is basically, you can also calculate your thermal efficiency based on the ideal gas relationship. Okay, the simplest is basically you can calculate your thermal efficiency using compression ratio. Okay, and of course using it. Well, this is for ideal gas. Okay, we assume that we are using the ideal gas relationship. So this pretty much just to show you, the higher the compression ratio, the higher the thermal efficiency. But in the real world, in the real case, it's not due to knock. Okay, so we are pretty much being limited because otherwise we would definitely get a higher thermal efficiency by increasing the compression ratio. But unfortunately, because of knock and so on, so we are limiting the compression ratio. okay, to prevent knock from happen. And when we limit the compression ratio, definitely your thermal efficiency also reduces. Okay. Okay, that is your auto cycle. I won't go into diesel cycle yet. I will postpone this next week. But towards the end of this slide, you can actually download this slide in e-learning by now. There's a question. Okay, there's a problem for you to some exercise on the thermodynamic analysis. So I'll just go through the question very quickly. A 2500cc four-cylinder spark ignition engine operates at 3000 rpm with wide open throttle. The engine has a compression ratio of 8.6 to 1, mechanical efficiency of 86% or 0.86, okay, and the stroke to bore ratio as stroke divided by bore is 1.025. The engine operates with air fuel ratio at 15 to 1, a heating value of 44,300 kilojoules per kg, which is already given to you, and combustion efficiency of 100%. Okay, it's one, in other words, but it's just an idea, just for learning purposes. But there's no such thing as a combustion efficiency at 100%. At the start of the compression stroke, conditions of the cylinder combustion are 1 bar and 60 degrees Celsius. So, in other words, if you look this carefully, at the start of the compression stroke, conditions of the cylinder combustion are 1 bar and 60 degrees. So, if you relate this start of the compression stroke, okay, you need to carefully determine where does the 60 degrees and 1 bar position. Is it in intake or compression? Think about it, okay? Sorry. So that actually gives you what is the P, which is 1 bar, and also T. So ask yourself, is this T1 or T2? Is this P0 or P1 or P2? And where does this actually position? Is it in intake or the compression? So, okay, think about it. Okay, and then what the question asks you to do is basically do a complete thermodynamic analysis of this engine to determine what is T1, P1, V1, T2, P2, V2, T3, P3, V3, T4, P4, and also V4, and so forth. So what you should do is basically first things first, you need to draw the PV diagram as what I've shown you just now, and go through each of the 6 processes. Then if you go through each of the 6 processes, then definitely you will able to calculate T1, P1, V1, and so forth. Okay, and then of course once you do the thermodynamic analysis, the 6 processes, you should be able to understand what is the network, thermal efficiency, mean piston speed, okay, brake work, torque, friction power, BMEP, BSFC, and also volumetric efficiency. So those are some of the questions that will ask you, that will require you to go to some of the lectures on those slides from previous ones. Okay. But first things first, just follow accordingly from A, B, C, D, E, F, G, because each of the questions, each of the answers from each of the sub questions will help you to determine parameters for you to use to calculate the following questions and so forth. Okay, so try this one first. Okay, I will give you. Okay, give me few days for you to give you for me to share you the answers for each of the questions over here so that you can actually compare whether can we get, I mean, and can you get the same answer or not? Okay. In the case of where you cannot get the same answer, then only you can come and see me lah. Okay. But if you manage to get the same answer as mine, then okay lah. Okay. Any question?
No, Doctor.
For the group activity ni, nanti kita kena submit ke apa? Doktor?
Sorry.
For the group activity, kita kena submit ke? No?
Tak payah. This one no. This one I purposely put group activities so that at least if you can work between 3 to 5 people and learn together lah on this.
Okay.
This one is not for you to submit. This one just to make sure that you know what if you just to make sure that you all know how to do thermodynamic analysis.
Mm-hmm.
But I'll share you the answers from A to J nearby in few days time.
Alright. Okay.
So any more questions? Okay, I think this is quite straightforward. I think mesti tak sabar-sabar nak try this question.
One question, Doctor.
Yeah.
In the slide, you said that intake at 1 ATM, but then higher if fuel injected. Maksudnya, the one in the one that we are learning is not FI ke, Doctor? Carbureted.
Yang mana?
In the slide, I read it in my notes. Intake, for 6 to 1 is intake at 1 at 1 atmosphere lah.
Yeah. Let me change the. Are we referring to this one?
Yes, but this one is diesel.
Okay. Oh, sorry.
Okay.
Okay. Go. Okay, continue.
I think atas lagi kot dia punya slide this one. But kenapa doktor cakap higher if fuel the pressure pressure for P6 to P1 ni is higher bila lagi tinggi bila fuel injected?
Bukan fuel injection, force induction.
Force induction. Okay.
Force induction. Because of the boost.
Okay, let me just. Okay, sorry.
I think saya silap pronounce kot tadi. Sorry. Force induction.
Okay. Itu je lah.
So this one you cannot understand without doing the exercises. So you all need to do the exercises, yeah. So the best is for you to I would suggest for you to work in groups, okay? Work together and learn this one. This is basically a typical question that will be asked you either in your test or also exam. Looking at this question, you looking at minimum answer sheet you will spend dalam 2 pages. Termasuk you nak lukis the graph and everything and formulas and everything. So by the time you reach to J, you already end of the second page of your answer sheet. So it's quite a long process, but it's quite straightforward. Once you get to know, once you're familiar with it, this is easily 10 marks in your exam. Easily 10 marks. Or probably more. Okay. So this is quite straightforward. I already told you that this is a common question in your test exam. Okay, if there's no more questions, okay, last. Do you have any questions before I end this session?
No, Doctor.
Okay, thank you very much, everyone.
In the future, for our class malam, we will end at 9 because of.
No, only for tonight.
Only for tonight. Alright.
Only for tonight.
Okay.
So okay. Again, for those yang belum who hasn't submit your assignment 1, please do submit before 12. because after 12 I won't receive anymore. We'll close the drive. So please make sure you submit before 12. For those who already submit, the 27 students, thank you very much for submitting. I really appreciate it. So you can download this slide in the e-learning, okay? But if there's I will provide you the answer for this exercise in a few days' time. Other than that, thank you very much. And for all the Muslims, selamat berpuasa dan selamat bersahur. So, okay guys, thank you very much. Bye-bye. Assalamualaikum warahmatullahi wabarakatuh.
Thank you,
Salam, thank you,
sir.
sir.
Thank you,
Thank you, sir.
Thank
Thank you.
Selamat berjaya.
Sir,
Doktor.
Doctor,
Yes.
I'm Lim. I mislooked the assignment one. And then
Okay.
now I need to upload, but the Google Drive send it the permission.
Okay, let me share you the link. You already, you have the link, right?
I have the link, but he said need the permission to access.
Oh, okay, permission to access. Okay, let me share you back the apa? Let me share you back the link. Hold on.
Doctor, thank you, Doctor.
While I'm doing that, besides Lim, anyone else wants to answer? There was somebody who wanted to ask something.
Doctor,
Yeah.
this is not I just actually wanted to ask whether is there any website where that we can sort of like find any examples of
Oh, okay. It's I think
combustion engine problems.
yes. You can download the. You can try to download the book lah. Unfortunately, if are you in campus?
No.
No, okay. Because the textbook is in the library. You can borrow the book. But I will give you the name of the book. You can try to download the book if it's available.
Okay, I sort of take a look of the book at is it called Engineering Fundamentals of Internal Combustion Engine?
Who's the author?
Willard
Betul tak?
W. Pull
That's the one. That's the one. Yes, you can use that one.
Okay.
Because in fact, actually, most of the questions in your test and also exam is actually inspired from that book.
Okay, I see.
So there's few examples you can follow there.
Oh, I found one, sir.
Hmm?
I found the book where I can find in the library.
Pandai lah.
Okay.
Hmm.
Okay, thank you, Doctor.
Sir,
Alright.
I still cannot upload the file.
Yeah. I'm trying to apa? To open the link so that everyone can.
Thank you, sir. Because I missed look the assignment already. Sorry,
Okay.
sir.
No worries. Luckily, you asked me now. Okay. Okay, I put in the chat box. Why don't you try to go in? Tell me now whether you can access or not.
Sir, still cannot.
Still cannot. Okay, never mind. I will tell you. You email me your work. That's my email. claim.
Okay, sir. Thank you, sir.
You just email me. You got my email there, over there in the chat box?
Yes, yes.
Okay, just email me. Yeah.
Okay, sir. Thank you, sir.
All right. Bye bye.